Coming up next in this segment is an expert talk on the topic, improving outcomes with better techniques. AI systems can get better by usage of better techniques. For example, transformers have presented tremendous ability to generalize language and images. This session discusses cutting-edge AI techniques that show promise of better outcomes with the same computation and data. Our speaker for this session is Ashwin Rao, Vice President AI, Target, and Adjunct Professor, Institute for Computational and Mathematical Engineering, ICME, Stanford University. Ashwin leads Target's global artificial intelligence team responsible for products involving demand forecasting, inventory planning and control, price optimization, personalized recommendations, search and marketing science. He's also an adjunct professor, like I just mentioned, in applied mathematics, that is ICME at Stanford University. A pleasure to have you here with us this evening. Ashwin, over to you.
Thank you, Justin. Okay, so today I'm going to talk about the topic of better outcomes from improved techniques. So there is a tremendous amount of buzz in the industry today about the potential of AI to solve important business problems in efficient and robust ways. There is indeed some exaggeration in the promises of AI, but there are a few techniques that have emerged which show great promise. Today, I will be talking about the top 3 techniques that I find quite valuable in terms of creating outsized business impact. But apart from the immediate concrete benefits of these 3 techniques, I find them exciting for the long-term prospects for AI. This is because these 3 techniques are significant steps towards developing human-like intelligence, which is really the original goal of AI. Let me list the 3 techniques first, and then I will spend about 5 minutes each explaining in simple and intuitive terms what these techniques are and why they're significant. So here are the 3 techniques: embeddings, causality, and reinforcement learning. Let's start with embeddings. When a neural network is trained, it captures the objects that it is learning about in a compact numerical representation that goes by the technical term embedding. The objects captured by embeddings could be anything: words, images, products, people, really anything for which we have data. If I train neural networks with very detailed data of what you do on your laptop, inside these neural networks, I will find these embeddings, really encodings that capture what kind of TV shows you like, how much time you spend composing emails, and even your attention span on video calls. The embedding for the kind of movies you like to watch might look like a sequence of 30 bits, but this numerical code has some serious intelligence inside it. It actually understands, say, that you're a scholarly person who likes watching long documentaries. And it understands that on Fridays, you make an exception for slapstick humor. Another embedding, say on your typing patterns, will recognize that you're obsessive about grammar and punctuations when writing emails. And it would connect this to your interest in watching documentaries about the English language. Hell, even your spouse might not know all this about you. Naive technologies do not possess this kind of semantic intelligence. Naive technologies simply parrot information. They don't understand nuances and subtle relationships. So while embeddings technology can describe your interests, preferences, and personality in a very interesting manner, a naive technology would simply describe you in a superficial and boring manner. It would just list your name, address, maybe the model of your laptop, the apps you have installed, and the hours of the day when your laptop is on. In other words, naive technologies have a flavor we associate with machines, whereas embeddings technology have a flavor we associate with human intelligence. The power of embeddings comes from the fact that we can use them to solve a whole range of problems in an efficient and robust manner. I could use this embeddings for your laptop usage to determine your suitability for different jobs. or I could use it to market the right kind of kitchen appliance to you. Technically, this means that the same embedding can be used as an input feature into neural networks to solve a wide variety of problems. In fact, automated feature creation using embeddings has already proven to be a game changer in natural language understanding, in computer vision, and in recommendation systems. We've seen just the tip of the embeddings iceberg yet. Expect some really powerful things with this technique in the future. Okay, so now we'll move on to the second type of technique, causality. So far, machine learning has been a game of identifying patterns, of identifying how often do things occur in tandem. The technical term for this kind of pattern recognition is correlation. Mastering the correlation game with machine learning has indeed been revolutionary for image understanding, language understanding, and even for playing games like chess. But when it comes to real-world problems like predicting the stock market or the elections, the correlation game is not enough. We need to master the causation game. Let me explain this with a classical example. We've observed that people who've slept with their shoes on wake up with a headache. Correlation-based technology like today's neural networks might end up concluding that somehow shoes are to blame for these headaches. But if I present you with this information, you will be quick to tell me that the people who've been sleeping with their shoes on were likely stone drunk and hence woke up with a hangover. You have this insight because you are playing the causation game. The human mind is very sharp at understanding cause and effect and in making very sophisticated inferences by building up causation theories. Machine learning so far hasn't been good at this causation game. The technique of causal inference from data has recently gained steam and promises to complement the current state of affairs in machine learning with human-like intelligence on cause and effect. This will give us AI systems that will be adaptable and robust and will be able to explain their decisions to us humans in a manner that we understand. Let me explain this with an example from retail. We sometimes make a decision to remodel a retail store to make it look modern, attractive, better organized, and convenient to customers. This typically results in a boost in sales. But we typically want to understand what would have happened if we had not done the store remodel. We want to understand this to isolate the effect of a store remodel, which in turn will help us with decisions to remodel other stores in the future. Today's machine learning algorithms are not equipped to predict what would have happened if a store had not been remodeled. The technical term for this is counterfactual analysis. And this kind of analysis is possible only by playing the causation game. The correlation game is simply not enough. Counterfactual analysis enables us to build cause and effect theories in life and in business. Cause and effect theories are essential to deliver on the fancy promises of machines having human-like intelligence. Another type of question that is hard to answer today are the type where we actively intervene in a situation to influence a certain outcome. For example, it is very hard for today's AI systems to predict what will happen to the sales of a product if we increase its shelf space by 15%. Causal inference provides the tools and techniques to first express these types of questions mathematically and then answer these questions. In the past few years, fields like epidemiology, social sciences, and econometrics have used the mathematical framework of causality to explain counterfactuals and interventions. Very soon, we will have AI bots that will stop saying that shoes cause headaches and start advising us to drink plenty of water before we go to bed if you've consumed too much hard liquor. This brings me to the last technique, which is very close to my heart reinforcement learning, which I do research on. Perhaps the most exciting thing in machine learning today is the technique of reinforcement learning. Let me abbreviate that as just RL. RL is rapidly emerging as a powerful technique to solve complex business problems across industries that involve adaptation of decision-making to changes in observed information, while continuously steering towards the optimal outcome. Some important high-profile problems where RL is now working quite well are self-driving cars, robots performing domestic tasks, and strategy games. These signs of success point to a future where RL algorithms will have decision-making abilities far superior to humans. It is important to understand what RL aims to solve rather than the more opaque view of RL as a technique to learn from data. RL aims to solve problems that involve making sequential optimal decisions under uncertainty. The applications are endless. In my own research, I've had the opportunity to look at a dozen important applications from retail and finance. These, I'll just name 4 of them. Firstly, inventory control, which is the problem of moving inventory from suppliers to warehouses to stores in the right quantity and at the right time, taking into account the uncertainties in customer demand. Price control, the problem of determining the right prices to set for each product one would sell at various stores, taking into account knowledge of how customer demand would react to price changes. Portfolio management, the problem of figuring out how much money to allocate to different assets in one's portfolio, taking into account future expectations of the returns and risks associated with these assets. High frequency trading, the problem of adjusting one's bid and ask prices on electronic exchanges, taking into account the market's likelihood of transacting with you for different bid-ask spreads. The common aspect of these problems is that one has to constantly adjust one's actions based on the evolving situations, taking into account randomness in future outcomes. So now let me explain how RL works by illustrating the brain of my favorite cricketer, Dhoni. Imagine Dhoni is in the middle of a tricky run chase. 30 overs left, 200 to make, 7 wickets in hand. At each ball, depending on the bowler and depending on the field placement, Dhoni has to decide whether to play carefully or push for a single or take a bit of risk in going for a boundary. This risk-reward trade-off is the action of the RL algorithm that is running in Dhoni's head. Mind you, Dhoni's RL algorithm has been trained not just based on his own past experiences with run chases, but also by watching in person and on TV thousands of such run chases, from gully cricket to international cricket. During the training of his algorithm, he has frequently tried hitting a straight 6 of an overpitched ball against the medium pacers. This action has worked well for him. So this action in specific game situations has been positively reinforced in his brain. So when Dhoni hit that winning 6 in the World Cup final, sending the nation into raptures, it was the result of Dhoni's finely tuned RL algorithm paying rich dividends. On the other hand, Dhoni has tried to hook bouncers against fast bowlers and has probably failed to pull it off in previous matches. That doesn't mean he won't try it again, but each time that action fails, it is negatively reinforced. And after a while, the hook shot against the fast bowlers will disappear from his portfolio of shots. The way Dhoni's brain has been trained is exactly how an RL algorithm gets trained for the various problems I described earlier. Indeed, RL is inspired by how humans actively learn through a process of trial and error by prioritizing actions that seem to work well and deprioritizing actions that don't. This might seem laborious and inelegant, but some clever mathematics enables us to develop efficient RL algorithms that learn fast and drive towards the optimal actions. Lastly, I want to tell you that the most exciting thing for us is that we are likely to have future AI systems that blend together all these three techniques: embeddings, causality, and reinforcement learning. In fact, if you think about it, this is how our human brain works as well. We bring together different powerful ideas to solve problems. This concludes my talk. Thank you for listening.
Thank you, Ashwin. It was a pleasure having you here with us, and thank you for that amazing presentation.